Hi everybody, today I'm going to show you how to model check first order logic on structurally sparse graph classes. This is joint work with Dreier and Sebastian Siebertz, and I am Nikolas Mählmann. In the first order model checking problem, you are given a graph G and a first order sentence phi, and you want to decide whether or not phi is true in G. Why do we want to have an algorithm for this problem? Because you can view it as a general purpose algorithm that solves many problems, namely all the problems you can formulate in first order logic. For example, the dominating set problem, you can write it as a first order sentence. There exist k vertices such that for every vertex y is either contained in or adjacent to the set of k vertices. However, this flexibility comes at a price. If we assume the exponential time hypothesis, then we cannot model check faster than n to the q, where n is the size of the graph, and q is the quantifier rank of phi, which is the naive algorithm where we just branch over all the vertices in the graph for every quantifier that we have. So now the question becomes, on which classes can we do fixed parameter tractable model checking? And this means model checking in time that is polynomial in the size of the graph, but might have an arbitrarily bad dependence on the formula phi. One important family of graph classes where you can do this efficient model checking are the nowhere dense graph classes. The class is nowhere dense if for every r there exists some k such that C does not contain the r subdivided clique of size k as a subgraph. On the right side you see, as an example, the 2 subdivided clique of size 4. We start with a clique of size 4, those are the red vertices, and on every edge we placed 2 subdivision vertices. This notion of nowhere density, it generalizes many other important notions of sparsity, such as bounded degree, bounded tree width, planarity, and excluded minors. And at STOC 9 years ago, Grohe, Kreuzer, and Siebertz showed that for monotone classes of graphs, which is classes of graphs that are closed under removing vertices and edges, nowhere density is exactly the limit for first order model checking. If the class is nowhere dense, you can do the model checking in almost linear time. Otherwise, it is AW star hard. To go beyond sparse graph classes, we lift this monotonicity condition and we now only ask our classes to be hereditary, that is, only closed under vertex removal. And one thing you could ask is, how can we produce hereditary classes from well-behaved sparse classes? One way to do this is by using first order transductions. Those are combination of coloring and interpretation and taking an induced subgraph. So what we do is we put some colors on this graph on the left, and now we use a first order formula which specifies our transduction to redefine the edge relation for the new graph. And in our case we say connect every 2 vertices that are both red and a distance exactly 3, and this will connect the left vertices that are red with the right vertices that are red. And then we can take an induced subgraph so we can delete those green vertices. Now we can use those transductions to extend our graph classes, and we define structurally nowhere dense classes as those classes which can be obtained by transductions from nowhere dense classes. Another property that is defined using transductions is monadic stability. This is a property that has been studied in model theory even since the 80s. And instead of saying we transduce from something simple, we say we cannot transduce to something complicated. And we say a class of graphs is monadically stable if and only if it does not transduce the class of all half-graphs. So what is a half-graph? Half-graph is the graph equivalent of a linear order. The half-graph of size k is made up of 2k vertices, a1 to ak and b1 to bk, and we connect ai and bj if and only if I is smaller or equal j. So there you really see why it is an order. What is the relationship between those two notions? Every structurally no-dense class is also monetically stable, and it is conjectured that they are actually the same, and also every monetically stable class is structurally no-dense. So here's another view on the properties we have discussed before. On the left side you see in green a column that is made up of sparse properties, with nowhere denseness being the most general property being on top. So the arrows symbolize containment. In the middle column, the yellow one, you see the structurally sparse notions, with structurally nowhere dense being on top together with monetic stability, where we do not know whether they are the same. And on the right hand side, you also see dense properties which are even more general than the structurally sparse ones. So there you have, for example, clique width, twin width, and in the top right corner, monetically NIP, a notion that generalizes all of this, but which will not be the focus of this talk. So what do we know about model checking? We know that this left-hand side column, the nowhere dense classes, that they are tractable. And since recently there's also an algorithm for classes of bounded twin width, which also covers a big portion of this map. However, this result is conditional, as it requires as an additional input a witness of bounded twin width, and we do not yet know how to compute it efficiently. So now I can state our result. We show that on every structurally nowhere dense class, first order model checking is fixed parameter tractable, and our algorithm also almost works for monetically stable classes. The only thing that's missing there is a proof that those classes admit sparse neighborhood covers, a condition I will describe later in the talk. So in the map of the universe, we expand the tractability of model checking to also cover this middle column. And one thing to note is that our result is unconditional and we do not rely on any additional pre-computed input. The rest of the talk I want to use to show you how our algorithm works. And one central notion in our algorithm will be that of a flip. And this is an operation which you can do on a graph by selecting a set of vertices and complementing the edges inside the set. So I've brought you an example. Here's a graph G, and in blue I select some vertices, the set I call F, and now I flip the set F. If I have two vertices and they are both inside the set F, if they are connected by an edge, I remove that edge, and if they are not connected by an edge, I add an edge. So I flip the adjacencies inside the set. And this operation is reversible. So if I perform the same flip twice, then I will get back to my original graph. But also from the perspective of first order logic, flips are a very tame operation. For example, instead of asking whether G models phi, you could ask whether the flipped graph models a rewritten version of phi. How do we do this rewriting? Instead of asking is x connected to y, we rewrite this atom with is x connected to y XOR are x and y both contained in the flip set. And in order to do this, we have to mark this flip set with a unary predicate inside the graph. You can think of this as putting a color onto the graph. And then we have G models phi if and only if the flipped and colored graph models phi hat. Flips are the basis of the following game characterization of monetically stable classes of graphs called the flipper game. The flipper game is parameterized by a radius r, and it is played on a graph G in rounds by two players, flipper and localizer. And in every round, flipper performs a flip on the graph, and localizer on the flipped graph chooses a center V and keeps only the vertices which are at radius r of this center that they chose. So localizer localizes the graph to a radius r ball in the flipped graph. And due to this localization process, the graph shrinks and flipper wins once the graph only consists of a single vertex. I will give you an example play of the radius 2 flipper game. So we start with this graph, and it's first flipper's turn, and he chooses a set to flip. And in this case, flipper is going to choose the entire graph, so he will take the complement of the graph. And already looks a little bit simpler. Now it is localizer's turn. Localizer chooses a center, and we only keep the vertices which are at distance at most 2 to the center. So the graph shrinks a little. And now it's again flipper's turn. Flipper flips those 3 vertices. So a new edge will be introduced and 2 will be forgotten. This is the flip. And now this bottom right vertex, it became disconnected. And now when it's localizer's turn, it will disappear from the arena. Again, it's flipper's turn. Flipper will, by his flip, destroy this triangle. Localizer's turn. We are only left with a single edge. This flipper can flip away as well. And with the next localization, the graph has shrunk to a single vertex and flipper wins. In a recent paper, we showed that monetically stable classes of graphs can be characterized by the flipper game. We have that a class of graphs is monetically stable if and only if for every radius that we play the game with, there exists a bound of how long the game will take for flipper to win. And this bound, it does only depend on the radius. It does not depend on the single graph from the class that you pick. So you can play on arbitrary large graphs. If they are from the class C, then you are guaranteed to win in L rounds. And the nice thing about this is that the proof is constructive, and we can compute flipper's winning strategy in quadratic time, actually. We now want to use the flipper game in our model checking algorithm. Our goal was to decide whether or not phi holds in the graph G. And the idea is that we do a recursive approach that works by induction on the remaining number of rounds to play for the flipper game. And we know that if we use this approach, then the recursion depth will be bounded as long as we have a monetically stable graph class. And the base case is very easy. If there's only one remaining round, then the graph has size 1, consists only of a single vertex, and we can brute force our problem. So how do we go into the induction? We have to somehow make progress in the flipper game, and this means we have to do some flipping and some localizing. We have to do some operations that simulate flippers and localizers move. And the flipping is easy. We can use flippers winning strategy in quadratic time, compute a progressing flip, and we can also rewrite our formula phi such that it holds on the flipped graph if and only if the original formula was true on the original graph. So the question becomes, how do we localize, and maybe also which radius r should we even play the flipper game with? In order to localize, we now look at guarded formulas, and we say a formula is guarded by a family of sets if each quantifier is either of the form there exists some x, and x must be an element of some of the guarding sets, or for every x inside the guarding set something holds. And the observation is, if we have a graph G and we have a formula that is guarded by this family, then we actually don't care about the vertices that do not appear inside any guard set. So if we evaluate psi on G, we get the same result as if we evaluate psi on the induced subgraph, where we only keep the vertices which appear inside the guarding sets. Now, if we take a look at the graph, and let's say our formula psi, it has guarding sets U1, U2, and U3, we can look at how do those guarding sets live inside our graph, and they might overlap, they might be disjoint, they might be connected or might be not connected. But the nice thing is, if they embed into a bounded radius, say radius r ball, inside our graph G, then we could just evaluate the formula inside this radius r ball, and this would give us a way to localize for the flipper game. So our goal will now become to efficiently compute the formula psi such that it is equivalent to phi on the graph G, and it should be a Boolean combinations of formulas such that each component is guarded by a family of bounded radius in G. We will not be able to compute a single guarded formula, but a Boolean combination is good enough. If we achieve this, we can check the single component separately and then aggregate the result. In order to guard our formula, we will need lemma about local types. I won't give you the precise statement, but I will explain using this picture. So let's say you have a graph G and you have two sets inside, A and B, and they have a large distance from each other. So distance bigger than 2 to the q. So what does this mean? If we take a look at the 2 to the q minus 1 neighborhoods of those sets, they don't touch. So we have the red neighborhood of the A set and the blue neighborhood of the B set. And now what I want to assume is that the red part of the graph and the blue part of the graph have the same q type. So what does this mean? If we restrict the graph to the red part, then it will satisfy the same formulas of quantifier rank at most q as we would have if we would have restricted to the blue graph. And now we assume we have a formula psi, which has quantifier rank q minus 1. Then what we will get is that inside the A set there exists an element u which satisfies the property psi if and only if there's an element v inside the B set which satisfies this property. And in order to prove this, you need to use a local variant of the Ehrenfeucht-Freisee games for first order logic. And we want to use this property in the next step to argue that only one of those sets, A and B, will be important for us. Let's say the formula we want to model check has the form there exists some x which satisfies the property psi. And this first quantifier, we want to guard it by a local set. What we can do is we can enumerate all the possible 2 to the q neighborhoods inside our graph, and we can write our formula as a disjunction of guarded quantifiers and put one disjunct for every possible neighborhood. And since we know that the x we are searching for has to be in some neighborhood, this formula will be equivalent, and every quantifier will be guarded by a local set. However, the problem is, since there are so many possible neighborhoods, now our formula has grown in size, which depends on the size of the graph. This is not very nice. We want to rewrite our formula, but it should not grow in the size of the graph, but only in the size of the original formula. So what we are doing is we do not keep all the neighborhoods, but we keep only one neighborhood of every q-type. And now, by the local type theorem, what we have is that if two neighborhoods have the same q-type, then either both will contain a fitting witness x or none of them will do. So the formula we get, it will still be equivalent. What we have now is that the number of neighborhoods we keep only depends on q, because for a fixed quantifier rank q, there's only a fixed number of q-types that we need to consider. And in order to do this, we actually need to compute those q-types and compare them with each other. This we can also do because we are only interested in the q-types of local sets. So we can recurse into a local component, and this is making progress in the flipper game. By induction, we can do it. So here we are playing the radius 2 to the q flipper game. This is very nice, and it tells us how to guard a single quantifier. If we want to guard all of the quantifier, we have to do an induction and extend this result to also work with parameters. Now we have all the ingredients to play the flipper game for radius 2q. We know how to flip, and we know that we can localize by computing the q-types of 2 to the q neighborhoods. And if we turn this into an algorithm, this will give us the following recursion tree. We have blue nodes where we play flipper moves, and then we branch into 2 to the q neighborhoods, which are the green nodes. By monadic stability, we know the depth of this recursion tree is bounded by some function of q, which is some function of the formula we are model checking. However, the issue is the branching is way too big. We branch into all the neighborhoods, and we get an O of n to the f of q algorithm. This is even worse than the naive n to the q algorithm. So recursing into every 2 to the q neighborhood individually is too expensive. So the idea is to cluster nearby neighborhoods. And we do this by a neighborhood cover, which is a set of clusters. Each R neighborhood is contained fully in one of the clusters at least. Each cluster itself embeds into a bounded radius set, and every vertex appears in at most d clusters, which is called the degree of the cover. We say a cover is sparse if the degree is at most n to the epsilon, for every epsilon bigger than 0. And if we sum up the sizes of the clusters of a sparse neighborhood cover, then we get size n to the 1 plus epsilon. For our recursion tree, this means if we choose epsilon small enough, then also the recursion tree will have size n to the 1 plus epsilon. So this solves our problem of the branching. The only thing left to show is that we actually have those sparse neighborhood covers for structurally nowhere dense graphs. This is what we do, and the proof utilizes a tree decomposition from an earlier paper. And we also need to compute the neighborhood covers. For this, we give an approximation algorithm, which gives a log n squared approximation, which is good enough for our case, and the proof uses randomized rounding of an LP solution. Combining these ingredients, we get the FPT model checking for structurally nowhere dense classes. For monetically stable classes, we are still missing the neighborhood covers. We conjecture that they exist there as well, and in this case, our algorithm would also work for monetically stable classes. Thank you for listening.